Hi, welcome to my channel. I'm your host GL, and today I'd like to talk about decantation. Decantation is pouring off a liquid from a container while leaving the solid or denser liquid behind, while filtration uses a filter to physically separate solids from liquids. You know, it's kind of like when you're making a cup of tea and you accidentally get some loose tea leaves in your cup. With decantation, you'd carefully pour the tea into another cup, leaving those pesky leaves behind. Filtration, on the other hand, would be like using a tea strainer to catch all the leaves. Both methods get the job done, but they work in different ways, just like how you might dodge a water balloon or use an umbrella to stay dry. Two different solutions to the same problem. In cooking, we often use decantation when making chicken soup, where we gently pour off the clear broth from the top while leaving the fatty layer behind. This is something my grandmother taught me, and it's a perfect example. When you make chicken soup and refrigerate it, that layer of fat rises to the top. Now, if you want a leaner soup, you don't need any fancy equipment. Just your steady hand and a good eye. It's like playing that classic game Operation, but instead of buzzing when you make a mistake, you just end up with a greasy soup. We also see this in winemaking, where they carefully separate the clear wine from the sediment. Pretty neat how something so scientific happens right in our kitchens, isn't it? Decantation works best with mixtures where you have either two liquids that don't mix, like oil and water, or when you have a liquid with insoluble solids that have settled to the bottom. Think of it like a middle school dance, where boys and girls stay on opposite sides of the gym. They just won't mix. The same thing happens with oil and water, they naturally separate into layers. Or imagine a snow globe after it settles. All the glitter sinks to the bottom, making it perfect for decantation. In both cases, the key is having components that naturally want to separate and stay separated. The better the separation, the easier it is to pour off one layer without disturbing the other. The basic steps are, first, let the mixture settle completely. Second, tilt the container slowly at an angle. Third, carefully pour the top liquid into another container while watching the separation line. And finally, stop pouring when you reach the unwanted layer. I always tell my students to think of it like sneaking past their sleeping cat. You've got to be patient and move very, very carefully. Rushing the process is like trying to run past that cat. You'll definitely disturb things and mess up the separation. The angle of the container is crucial too. Too steep and you'll get a messy splash, too shallow and it'll dribble down the side. It's like pouring the perfect soda. You want that sweet spot where it flows smoothly without fizzing over. And by the way, if you are enjoying the video so far, do me a quick favor. Hit that like button. Really helps support the channel, and it only takes a second. The main limitations of decantation are that it requires components with significant density differences, needs time for settling, can be imprecise, and isn't suitable for mixtures where particles remain suspended or where layers separate very slowly. You know, it's like trying to separate M&Ms by color while wearing mittens. It's possible, but not very precise. In my lab, I often tell students that decantation is like trying to eat soup with a fork. There are just some things it's not meant to do. For example, if you're dealing with an emulsion like milk, where the fat droplets are suspended throughout the liquid, decantation is about as useful as a chocolate teapot. And don't get me started on the time it takes. Sometimes waiting for particles to settle is like waiting for your teenager to clean their room. It could take forever. Density difference is the driving force behind decantation. The greater the density difference between the substances, the easier and more effective the separation will be. Picture this. If you throw a bowling ball and a beach ball into a pool, they'll separate instantly because of their huge density difference. That's what we want for perfect decantation. But if you throw in two similar rubber balls, they'll both just float around together. In my class, I demonstrate this with a layered density column using honey, water, and oil. The students love watching how these liquids stack up like a liquid rainbow. Each layer clearly separated based on density. It's like a heavyweight boxer trying to mix with featherweights at a party. They naturally end up in different layers. Yes, decantation can separate solids from liquids, but only when the solid particles are heavy enough to sink and form a distinct layer at the bottom, like sand in water or coffee grounds in coffee. Let me tell you about my morning coffee routine. I once tried making cowboy coffee where you just throw the grounds directly into hot water. When you let it sit, the grounds sink to the bottom like students rushing to their seats when the bell rings. Then you can carefully pour off the coffee, leaving the grounds behind. But here's the funny part. The first time I tried this, I got impatient and didn't let it settle properly. Ended up with a mouthful of grounds. It was like trying to drink a sandbox. Now I wait patiently, just like when I'm waiting for my students to quiet down after lunch break. Temperature affects decantation by changing the density and viscosity of liquids. Higher temperatures generally make liquids less viscous and can speed up the separation process, while lower temperatures can sometimes help by making density differences more pronounced. It's similar to how we all move slower on cold winter mornings and faster on hot summer days. In my lab, we once did an experiment separating used cooking oil from water. When the mixture was cold, it was like watching paint dry. Everything moved in slow motion. But when we warmed it up, the separation was faster than my students running to the cafeteria on pizza day. However, you've got to be careful. Sometimes warming things up too much is like adding sugar to kids. It can make everything too energetic and mixed up again. The key is finding that Goldilocks temperature. Not too hot, not too cold, but just right for your specific separation needs. If you're looking for exercises to test your knowledge, there is a link in the description for you. Thanks for sticking around till the end. If you enjoyed the video so far and want to see more content like this, make sure you hit that subscribe button. Thanks for watching.